How's everybody doing?
Good.
So, this is going to be a major geek out session. So just bring your technical hats on, right? I'm very privileged to have this trifecta of amazing panelists. Firstly, I'll introduce Ramin. Ramin is a true serial entrepreneur, right? Starting from he was part of Valio, and then I invested in Quantia, and now it's a amazingly company called Eliyan, which is really breaking the bottlenecks of electrical interconnect or copper. And I'm privileged to be able to work with Ramin over the years. Secondly, Matt Sysak, who once the data leaves, the immediate silicon package, it has to move at a speed of light, right? So Matt is really driving the most vital optical portions. And as CTO and of cloud networking at Lumentum, he leads all the technology initiatives and development, including things like high power continuous wave and co-packaged optics, and pioneering the dynamic optical circuit switching area. So his technical roadmap sits absolutely at the center of global AI hardware. Please welcome Dr. Matt Sysak. And then even more amazing will be Dr. Julie Eng. Julie is a highly accomplished executive who perfectly bridged the material science, the advanced optical and transceivers, and massive cluster deployments. As the executive VP of optical components and the CTO, Julie wears many hats of Coherent. He steers the technology strategy for the global giant in photonics and advanced networking substrates. Her team is leading the industry's change past the 1.6 terabit transceiver and deploying linear package optics. So I'm really privileged to have all three of these amazing thought leaders and technologists here. So now I want to make a kind of a maybe sacrilegious statement. So even though before, there's a lot of focus on, processing, right? Processor, CPUs, network processors. I believe the ultimate bottleneck to artificial intelligence now is no longer the raw speed of processing chips. The bottleneck is really now the interconnect. Now, you may argue that that's not the case, but hey, that's my position. So I'm very excited that, we, as Celesta, we invest in interconnect focused companies. As moving massive AI workloads across a cluster requires an insane amount of data transfers. Inside the rack, traditional copper signaling is running out of steam to a degree. So now there's going to be a kind of interoperating of copper, electrical signaling, and optical. I'm super excited about all the innovations that's coming, and that will be the topic of today's discussion. So starting off, I wanted to actually have a list of questions. So excuse me. I want to start with Julie. Question number one. So there are a lot of technical noise and jargons, right? So if as not all AI interconnects have the same requirements. If you look across, right, there's scale up, there's scale out, there's scale wide, there's scale across, and now the latest thing is scale in. So I would love to get a sense of what you think are really the required technology building blocks that really supports this trend of all these scaling. And then obviously after Julie, feel free to jump in, once Julie makes her point.
Great. Thanks, Steve. Yeah. So if you think about it, so all the scales that Steve mentioned are really optical interconnect replacing electrical interconnect, and that's actually happened all the way back since our first transatlantic calls. First, they were electrical, and then as the data rates go up, and the distances you need to transit stay fixed or get larger, you have to transition from copper to optical. It's the most efficient, cost-effective, and sometimes the only way to make that connection. So that happened first at transatlantic, then it happened across the United States, finally inside the data center. And now what we're talking about is the scale up, so inside the rack, scale out between racks, scale across between data centers, and now Steve mentioned the scale in between die on a chip. And I think when you look at that, that's a vast array of different applications. And so you might see multiple technologies for those applications, because some of those applications may be more focused on getting a ton of data through one fiber from one place to another, but others of them might be much, much more, say, inside the rack, much more focused on power consumption, latency, and cost. And so today, inside the AI data center, we have sort of three primary technologies, which are called indium phosphide, silicon photonics, and gallium arsenide VCSEL. And all three of those technologies coexist. And there's a reason for that. It's not because we all like doing too many things, because each of them kind of has an architectural strength and an architectural weakness. And you see them in different spaces. And so I think as we transition to, say, scale up, optics in the scale up and the scale in, I think you may see multiple technologies coexist that are each optimized for, one maybe for reach, and one maybe for power consumption and cost, but shorter reach, maybe one somewhere in the middle.
Great. Yeah, I think one of the other things that's pretty interesting is if you look across the networks, kind of like Julie is explaining, if you start outside of the network, you have kind of long haul, then you come inside of the data center where you're trying to connect racks together. You're trying to connect compute together to the backend network, where again, you're trying to connect a lot of accelerators to kind of scale up. If you kind of look at that topography, what you see is optics has been in kind of scale across applications where you're trying to connect distances for some time. It's also been in things like connecting racks for some time. And now we're starting to see it in kind of scale out. So kind of a lot of the core technology building blocks associated with connecting those things with optics already exist. I think one of the most exciting and one of the most interesting things that's happening, right, is this optics kind of goes to these smaller and smaller scales like Julie is talking about. It's not just about taking technology we know and scaling it. It's about introducing fundamentally new technology building blocks, which we may not necessarily have today. And of course, that's doubly true as distances get shorter and shorter as you think about scale up versus something like even scale in.
I guess Julie and Matt said it correctly. And for every application have their own requirement and needs and features that must be fit into that specific application. Like we can take like a simple example, like a motorcycle. It started maybe with street bikes, but mountain bikes or cruise bikes and so forth, each are basically, they have an engine with two wheels, but they have to be optimized for their specific application that need to serve. And same applies for, depending on, you want to go scale across the cost of the fiber because it goes hundreds of kilometers. That's more important, focusing on that and not so much on power and the cost of the transceiver. When you talk about scale outs, maybe somewhere in the middle, you don't have to spend expensive technology to put many lambdas or coherent lights into one fibers, but use DSP and PAM to kind of expand the bandwidth. But it's a balance between power and, of course, distance, because it's still distance are kilometers, like 2 kilometers and so forth. But then you come down to scale up and scale in, which are like within a rack or within a pod, that the reason is application is completely different. In fact, if you want to look at it, the reason that we have this notion of a scale in or scale up is because historically these things were all sitting on the same chip or on the same board. Because of Moore's law, that not enough processing power could fit into a single chip, people started growing the chip, became radical size, and then connecting them together with die-to-die connectivity. But there's so much or so many of these ICs that you can put inside the one package. Then you have to connect them through other means. There's been copper so far, like NVIDIA racks or the racks has been trying to stay with copper because the reliability of these connections are super important. You cannot drop links or so forth. And as a result, that's why NVIDIA is trying to put as many of these into one rack to all stay with copper. But as the number of these devices or GPUs increase and you have to go across multiple racks, then optics come into picture. And the requirement for scale up or scale in becomes reliability, becomes like one of the number ones. And then, of course, power and cost and availability, other things, because the amount or number of these are orders of magnitudes higher. So the dynamics,
Yep.
the whole fundamental changes.
So we set the stage for the next question. So now we've defined the opportunity, and if you believe me, the opportunity is huge for interconnect, right? Just look at the market caps of the companies represented here. So the opportunity is big. Interconnects actually consuming huge amount of power, right? That's going to data center. So the next question I have is where do you think is the bottleneck? And then by defining that challenge, the bottleneck, and also brings in the opportunity for both large companies as well as startups that want to drive leading edge technology. So that question I'd like to direct to Matt and get your point.
Yeah, the bottleneck. Well, I mean, if you kind of think about it, each network kind of has its own sort of bottleneck in a lot of ways, right? I mean, just think about something as simple as like scale across. You would think that again, the technology for that's been around for a while. I mean, coherent optics, kind of long reach communications, and there the bottleneck is really how fast can we deploy materials? How fast can we deploy devices? I mean, there's so much data moving around so quickly that even those networks have sort of unique bottlenecks. But I think, if we really focus on kind of, scale up, I think the bottleneck there is kind of, twofold. I think number one, there are just a lot of different people that have a lot of different ideas about what that network should look like. And a lot of people differentiate by creating different versions of scale up, different degrees of radix, different data rates, different styles of, how many GPUs you want to create, you want to connect together. So I think, one thing is, and one aspect of this bottleneck is, hey, look, how do we create some sense of like, what is a scale up network? And that may mean that there'll be a bunch of different technologies that are deployed all at the same time because everybody wants to continue to use, scale up network to basically differentiate. That's one aspect. The other aspect of where the bottlenecks are, I think, especially when you think about scale up, is around the size of the opportunity. If you think about just optics as a whole, right? Before AI, I mean, the total volumes associated with optics are nowhere near what they are today. And so there's this big sense of how fast can the industry scale? How fast can we develop and deploy things like indium phosphide capacity? How fast can we scale our fab capacity? How fast can the supply chain keep up with the demands from some of these huge interconnect opportunities? So I think really the bottleneck kind of stems from two things. I think, number one is this diversity associated with how people deploy that scale up network. And number two is really our ability to scale to meet the size of the opportunity.
Great. And then Julie?
Yeah, I think I agree with everything Matt said. Also, the speed, the pace with which we're having to innovate is just coming faster and faster. So I looked at it, and I looked at our data rates as a function of time because I felt like it was coming faster and faster. And I had to plot it on log plot, and it was growing exponentially. So we're having to introduce new technologies faster and faster than before. But at the same time, to Matt's other point, I looked at how long did we have until we had to deliver as a whole industry, the first 10 million units? And at 10G, we had like 15 years. And now we have like 4 years.
Yes.
So our manufacturing scale, as Matt said, it has to ramp. Well, the physical challenges are actually all getting harder. And so one of the biggest bottlenecks, I think, is because as Ramin said, that as you go to parallel computing, that architecture depends more critically on the interconnect, the performance of that system. So now the interconnect is not just a wire connecting two things together. It's actually a fundamental part of the architecture of the whole system, which leads to Matt's point about the diversity of solutions, because now it's like the AI data center it's a massively distributed supercomputer, and the optics is inside the machine. And so whoever designs that supercomputer, we have to have the technology to achieve that. So I think the pace is so fast. And then the fact that effectively the communication channel, if it's not high enough speed is bridling how many tokens you can get in and out, right? And so that has a big economic impact to it. And so just being able to transmit enough data from point A to point B and develop all that new technology and scale it on the time frames that's needed is one of the challenges.
Yeah. And absolutely, I totally agree. And there is a new, we come up with these phrases, memory wall, I/O wall, power wall, and there's a new term called copper wall. And it came mainly, I think, because of the limitations that copper ended up to have a longer reach. People want higher bandwidth, but higher bandwidth means shorter distance for copper. But at the end of the day, when the number of GPUs and so forth increases, in fact, we want longer distances. So what it means is that copper cannot service this. Now, we have to have a solution which is optical, but being able to provide the characteristics of a copper, but deliver that performance. And copper, one of them is reliability is number one. The other one is like power, being low power, another important factor, and also availability of supply. We hear a lot of supply shortages of indium phosphide. Now, if this has to go into optic, we go to scale up by 2x more volume, how the world can supply it. So those are the questions that need to be answered.
Again, you're setting me up for the next question, so thank you. So this is a question for Ramin, and might be a little bit controversial. So, historically, the optical industry has been really optimizing around speed, per lane speed, right? So for AI infrastructure, should we continue to push for faster lanes, or should we start optimizing more aggressively on power, latency, reliability, and cost of the delivery of the bits? So I'd love to kind of get your point of view on that, and then followed by Matt.
Sure. Industry usually, when it comes with a good solution, because it's been proven and they want to go in that direction, they basically everyone push in that direction as much as they can until they can't. Maybe about 10 years ago, we had, at my previous company, Aquentia, we had to start doing chiplet architecture for different reasons. And back then, for die-to-die connectivity, was something called XSR, which was like PAM4 serial and so forth. What I realized is that as much as PAM4 is good for high speed over cables, because it minimizes the number of cables you have, is not a good approach for die-to-die when you can have a lot of wires over there. You can use NRZ to reduce power as of the PAM4. You can have extra wires for redundancy and so forth, because die-to-die connectivity is effectively replacing the connections on the same chip. So it has to be super robust, super low power, and low latency, and so on and so forth. Now, as I mentioned earlier, now we are at the stage for scale-up that effectively scale-up connectivity is the same as die-to-die. So why not use the same approach rather than continue going PAM4? Use the same approach that I proposed about 10 years ago, and then end up UCIe, the whole world going in that direction. NRZ, single-ended with redundancy, so on and so forth, minimum latency. So I think that will be the right answer also for all the scale-up solutions and scaling solution moving forward, and especially when you have additional lanes, and these lanes are, I wouldn't call it free, but much cheaper than having a heavy-duty DSP behind each one of them. That will give you everything that you need to create this connectivity for scale-up.
Okay. And then maybe
and just to add, I think there's two different architectures, one which kind of takes fewer signals at higher speed, and one which takes more signals at lower speed. And you're kind of trading off different constraints. So in the higher speed one, you can use fewer, let's call it lasers, optics, fewer optical cables, but you pay a price. And the price you pay is you have a high-speed SerDes, which consumes power, and you may add latency depending on how you do it. And the other side, then, you get rid of that high-speed SerDes, so you can save power, which is very important in the data center, but you pay a price by having to have many lanes that have more fibers. And so there's kind of a trade-off between, call it package complexity and power consumption. And I think different applications might choose different solutions, but certainly power is very important, and anything that can minimize power consumption and latency is very valuable. And so that's why I think you do see some push toward the what we call slow and wide on the shortest reaches. On the longer reaches, again, as Ramin said, you might have a fiber that goes a long distance. You might choose to try to utilize the bandwidth of that fiber as much as possible.
Agreed. Yeah, Matt.
Yeah, I think very, very well said. I think maybe what I'd add is it just depends on the network. It depends on what you're trying to do. You know, I think if you think about some of the longer reach things, right, you would not want to send 100 cables like over 10 kilometers, right? It's not economically a great solution. And so from that perspective, when you're trying to go longer, you're trying to pack more bits into the fiber. You're trying to run higher speeds. So, you know, modulation formats like PAM4 make a lot of sense because you're trying to optimize for the system and the constraints associated with that system. Now, when you start talking about things like compute, when you start talking about things like scale up, the optimization is completely different. You're not trying to optimize for number of fibers. It's less of a constraint. You're really trying to think about things like cost, things like latency, things like reliability. And from that perspective, you go a completely different direction, right? You may say that over some of these shorter reaches, having a lot of fiber is perfectly okay, provided that gives me some architectural benefits, such as lane redundancy, failover, or something like reliability.
Great. Now, maybe I ask the audience, how many of you guys have heard of PAM4? Because this question is going to be okay. So I won't define PAM4, but it's a type of encoding that's used very commonly. So this question is for Julie. I told you this is going to be a geeky. So as line rates, right, go from 224G to 448G, how sustainable is the industry's reliance on these more and more complex PAN encodings? And then how do you think that's going to evolve? Is it going to basically go back to NRZ, or what will be the kind of potential architecture that evolves?
No, that's very important because, again, as I mentioned, we have to keep getting faster and faster and faster. And so you have two ways to do that. One way is you raise up the data rate of every lane, and the other way is you use more lanes. And so you multiply those two numbers together, that gives you your aggregate bandwidth. So historically speaking, we always tried to get up to the highest lane rate and then multiply the lanes when it was hard to go to the next rate. And so, but this jump between 200G and 400G, it's a big jump.
Yep.
So people, both Matt's company, my company, we've shown components that are capable of 400G. So optical components could be made today that can go 400G per lane. So we're actually limited today by the electronics.
Yeah.
That there's no one who's offering a 400G PAM4, or maybe they're just starting to offer the 400G PAM4. So I think that the hurdles get higher as the data rates get faster, and then that might. And when the hurdles get higher, a lot of times, what do you pay for that? Power consumption and cost, actually, right? And so I think for long distances, you'll still see people maximize the speed per fiber or speed per any media. But I think for the shorter distances, it's a big overhead to pay. And those PAM4 ICs generally, you know, they add latency. A lot of times people use FEC, so there's an overhead. And so I do see for shorter reaches, especially in the scale up domain or the scale in, like die to die, we do see a resurgence of interest in NRZ, I would say. So almost like going backward in data rate, but then doing it even in a more parallel way, like kind of a, you might call massively parallel way compared to what we've done in the past.
Great. And Matt, maybe any more comment on that?
I think it's been said pretty well.
Okay. So what micro LEDs, you know, being promoted over the last few years, kind of almost in a holy grail-ish. No, I'm not an investor in micro LED, but it's not to say I didn't look at it. So I'd love to get your point of view on some of these kind of new technologies that's coming up, and get your take on that. A question for Matt.
Yeah, kind of like I said before, I mean, I think there's this big diversity of the way people treat kind of these short reach interconnects. A lot of people differentiate that way. So it's very viable that network may have many technologies that find a home. I could completely see that. But the different technologies have a lot of trade-offs, and maybe we can just kind of talk through a couple of them and talk through some of the trade-offs that are associated with each. So kind of maybe starting from microLEDs, right? If you know the history of microLEDs, they've been around for some time. If you have a Garmin watch, I have a Garmin watch. MicroLEDs are in some of the most recent Garmin watches. They're also in headlights. So, they've achieved some commercial success. And what they're really good at is density. You can make these things very, very, very dense. You can have emitters that are spaced on the order of like a few microns. So density from a micro LED, at least from a raw emitter perspective, is pretty good for that technology. What they're not good at is they don't produce a lot of power, right? An LED by definition is omnidirectional, meaning kind of like a light bulb without a little lampshade, right? I mean, you turn this thing on, light kind of goes everywhere. So it's hard to move information from one place to the other because the power levels are kind of low. You need some kind of directionality associated with that technology. So that's micro LEDs. So you could imagine maybe the best home for something like that would be ultra short reaches that don't require a lot of power and can leverage some of the density that technology provides. When you step up a little bit, you go from maybe something which is on the order of less than a meter up to a few meters, right? This is where something like VCSEL technology becomes very, very, very interesting. If you have an iPhone, VCSEL technology is in your iPhone, and it gives you a sense of the deployment of that technology at scale. It's actually quite mature. In between, I think Julie's company and Lumentum, Coherent and Lumentum were two of the largest manufacturers of the lasers, the VCSEL lasers that go into that application. And one of the things that we're trying to do is reuse that technology specifically for some of those, mid-meter kind of reaches. And the reason is twofold. Number one, very, very, very high volume. That application, which exists inside of the phones, is a very high volume application. So the VCSEL technology is a perfect fit for that particular use case. That's one. And number two, depending on the technology you pick, what it can do is it can translate what a lot of people think about as edge shoreline density to a two-dimensional exit. So you can do things like take the VCSEL chips, take the detector chips, and flip chip them on top of electronics. You can go from kind of this one-dimensional limit into this kind of two-dimensional limit. And when you're talking about networks like scale up, really, it's all about density. It's all about getting a lot of information over a very small amount of space. So that's kind of the VCSEL technology. And then if you go one more step, right, as you go maybe from a couple meters all the way up to a few tens of meters, even to a few hundreds of meters, this is where something like silicon photonics starts to get interesting. Silicon photonics is really good. It can pack a lot of data down a single fiber, which is one of the trends we talked about earlier. Silicon photonics can leverage a lot of the laser ecosystem, that kind of is already in place, but it's very good for those longer reaches. So you can absolutely see kind of as like you look across some of the different applications and some of the different deployment reaches, all three of these technologies playing.
Great. And I'll move on to another technology that's, during the OFC, there was a lot of companies, startup companies trying to jumping into it, which is the optical circuit switching. So I'm seeing a lot of companies that's doing integrated, photonics, or they're doing MEMS, or doing a hybrid. I'd love to get your view on that because Google really started that optical circuit switching, but it's a very unique use case.
Yeah.
So the question I have is optical circuit switching something that's going to evolve and proliferate? And how does that, what does that mean for Ethernet? Right. So because it's definitely something that's kind of has to mix together. Maybe I'll start with Julie.
Yeah. I was when Google published about using optical circuit switching, they talked about an application that was a spine switch replacement, and they also talked about how much work it was to integrate it into their network, actually. And so I was surprised actually that I'm interested to hear if Matt was too, but about the breadth of customers that were interested in optical circuit switching and the pace with which those customers accepted that new technology. And it took me a while of talking to customers to finally figure out why. And the reason is how people are using an optical circuit switch is effectively as to reconnect the fibers inside the data center to maximize the uptime of the GPUs for different workloads. So if you think about it, it can, because all the fibers come into the circuit switch, and data that comes in on one fiber, you can send it out on any other fiber. So if you think about it, it's like a software-defined remeshing almost, you might use, I shouldn't use
Yeah.
that word, but changing of the hardware of the connections between the GPUs. So let's say this month you're training a large language model, like we saw in the data there about large language models versus inference, and you want to put all your GPUs on that large language model. But maybe 2 months from now, our customers want to train many small models, and they want to change how the GPUs are connected. Now they can just do it with a simple software command. And then I think that there's multiple technologies, as you said, all of which have pluses and minuses, and we implemented the technology we implemented, which is called liquid crystal, and we did it for a certain set of reasons. But I think overall that there's a set of specs in the data center, and any technology that meets those specs can get qualified. And for both Matt and I right now, our problem is not demand, it's a supply constrained market right now. It's a very, very fast growing market. And I think in the end, it's because fundamentally, it's allowing our customers to maximize the utilization of their GPUs, which is very, very valuable.
Great.
Yeah, you nailed it. That's exactly right. And if you think about it, like the way I like to think about optical circuit switch, kind of like Julie said, right? Today, it's kind of, okay, it's this master configurator, right? It can take a big cluster of GPUs and slice and dice it. If you have a reliability issue, it can work around the reliability issue. Like Julie was mentioning, if you want to go from training some very large model to some smaller model, circuit switching allows you to do that, which is absolutely fantastic. But that's just the beginning. That's where it starts. And so definitely we're seeing a lot of people not just think about circuit switching from that angle, but also think about, well, okay, now the technology is really hitting the data center. Now the scale of deployment is getting bigger. Where else can we use it? What other use cases do we see? And so people start talking about things like spine replacement. People start talking about network failover, right? Where it's not just about slicing and dicing models. It's about having an extra rack of stuff, So if my rack starts to behave in a way that I don't like, I'm like, okay, shut down this rack, just bring up a whole other rack, and then I'm on my way from a training standpoint. So even though we're seeing circuit switching kind of in this first implementation, which is this slice and dice, kind of again, as Julie was mentioning, that's not where it's going to stop. There's a lot more use cases of the technology that will happen as time goes on.
So maybe I should invest in the area. Next question is for Ramin. In the industry, there's always this, the electrical or copper camp, and then there's an optical camp. I actually look at it as a continuous thing, right? Because unless one day we have optical computing that will replace the CMOS or the digital computing, I think you always need that transition, right? And the two needs to work together. So Ramin, I'd love to get your point of view on the CPO, co-packaged optics, MPO, and really how this copper and electrical signal and optical is really intermingling in the bigger system.
Sure. So I've been a copper guy, electrical guy all my life. I mean, back in the 90s, I did the first PAM4, and I thought this is the way to go for a long time, and it did. It went for more than 20 years now. And I even went ahead and did like PAM16 and so forth for other applications like 10G base T. But I think at the end of the day, the environment, the medium, defines the limitation of how fast you can go. And right now we have a real bandwidth bottleneck, bandwidth wall for these GPUs to talk to each other. GPUs are going from maybe 10, 12 terabits to 25, 50, and the rate I see it, hyperscaler planning on 50 to 100 terabits per GPU. There's no way to get that kind of bandwidth out of the package. So with electrically. But when you go optics and deal with much finer fiber pitch and so on and so forth, it makes life much easier. But of course, as I mentioned earlier, it's all about how reliable, how power efficient and so forth you can build these things, because people stayed with electrical for a reason. It's reliability, power, and availability. Of course, copper are always available. And that's why we started looking into microLED about 2-3 years ago, and then it evolved into having the need to have more reach. That microLED had the limitation, evolved into looking into microVCSELs, and of course microVCSEL has its own challenges. Temperature of a VCSEL, if you put it so dense, that's one issue, and being able to put all these things in a very high crosstalk area, there are other issues and so on and so forth. So But I remember it was maybe about a year ago, I saw a presentation from Matt that kind of gave us the confidence to kind of say, oh, so we can go in that direction, and made us more bold to start talking about it more so. And I'm happy to see that right now, micro-VCSEL is one of the dominant paths to replace copper effectively.
So I actually have another 25 questions, but unfortunately, we're down to the actually 0 seconds. So last questions for the panelists, and I really appreciate you guys, is there are a lot of aspiring startups, and Matt, you told me you're tracking 80 startups, and maybe Julie, you're tracking 100 startups. I'd love to get a sense of what, looking forward to 2030, what are the really things that are on top of your mind in terms of technology innovation and what is coming kind of next, so that the aspiring entrepreneur and the startups can really derive their focus toward that direction. Maybe start, Matt.
Yeah, no, this is always a good question. I think when you're a startup, the one thing you should really think about is what problem are you trying to solve. I think sometimes startups, when they start out, right, they say, I have this wonderful technology, worked my whole, say, my PhD or my master's, or maybe you're a bachelor's and you're thinking about, I've done this wonderful thing, I really would love to find a home for the technology. I think the thought process has to be a little different, right? It's like, you really need to think of what problem does this solve specifically, and really get crisp and articulate about it. That's one. And then the second thing is not just what problem you're going to solve, but how are you going to solve it? And who is in the partnership list for you to go from, okay, here's my idea, here's the application, here's what I'm trying to do, here's how I'm going to do it. So really kind of thinking through those things. And, oftentimes when we meet with startups, regardless of what the technology is, it could be anything. It could be something in, say, circuit switching, could be something in high density interconnect, could be something in, who knows what, right? But a lot of times it's not just the technology, right? It's how mature is the thought process for the people who are behind the startup. How well can they articulate, and how well can they talk about, again, what problem are they trying to solve? How are they trying to solve it? And then how differentiated are they?
Great.
Yeah, I think that's our job, right? To figure out what's going on by 2030, which is not that far away anymore. It's only 4 years away. And so definitely I see a lot of interest now. We're already deploying. Obviously, we have deployed scale across, scale out. I see the new deployments of scale up happening like by next year. And so you say, well, what's after that? I think it is this scale in. Like, how do you solve this die-to-die optical interconnect problem as copper runs out of steam in that domain? And I think that those solutions are going to look very different than the solutions we have today. And some of them will rely on fundamental device improvements. Some of them will rely on packaging improvements. So I think both of those are valuable areas to work in for sure. And then I think actually thermal becomes very important. We have a lot of thermal materials in our company, silicon carbide and diamond, and we're just seeing a lot of applications of thermal in the data center. And then finally, last, there's many, many more, but another one is actually quantum networking, which is once you have like actual functional quantum computers, they can basically, there's a challenge that they break all modern cryptography, right? In your bank statements and your health records. And so how do you generate something that helps secure that data in the optical channel? So that's another
Very good.
A future thing, I think, that's interesting.
Very good. Ramin, last but not least.
But I don't get to see a lot of startups.
Well, you're busy.
But
you're busy.
yeah, they've been too busy. But general philosophy is that finding the right problem, finding where the real bottleneck is, and making sure that the solution is practical, like doesn't have so many risks. Because just at the end of the day, startups, there are already too many risks, and you want to limit the risk into one.
Yep.
Make sure there is no risk in the application and market. There is no risk in the or there's no risk in the implementation or technology and so forth. And so that's all we can add.
So I'll end on this note. In 2013, Andreessen Horowitz said that software is eating hardware. Given a old school hardware person here and a semiconductor person, I'm very happy to announce that hardware is now eating software.
Love it.
And I'm very, very happy. Thank you. Thank you.